DSN is the acronym for the Deep Space Network. We oversee the operation and maintenance of antennas that track all of the spacecraft that NASA has in space. And we operate in geostationary orbit and further out. So things that are really close to the Earth are tracked by other NASA networks. Ours is stuff that is in deep space, as the name suggests. What kind of data do we send? So we send data to the spacecraft, we call those commands, and then we receive data kind of three types. Science data, so that's instruments on board the spacecraft, things like images of a planetary surface, or seismometer readings from the surface of Mars, that kind of thing. We get health and safety data from the spacecraft. That's stuff like battery voltages, temperatures, stuff that tells us how the spacecraft are operating. And then we also get what's called tracking data. So that's data that tells us where a spacecraft is and how it's moving. So that's kind of a summary of what we do. How do we get started? So the origin and history of the Deep Space Network is about as old as the origin and history of spaceflight itself. So many of you probably know that the Soviet Union, Russia, was the first to put a satellite into space. That was Sputnik. But then the answer to Sputnik from the United States was Explorer 1. So you can see here in the picture, that's William Pickering, James Van Allen, and Wernher von Braun holding a model of Explorer 1. So what do you need to get a spacecraft in space? You need a launch vehicle, you need a satellite, and then you need ground stations. You need something to receive the data from that spacecraft. And so that was our origin. Ground stations. Will you go back on? Okay. So we were the ground stations for this first ever satellite launch for NASA. At that time, we had what was called our mobile tracking station. So that's a couple of tractor trailers and a 10-meter dish that's completely portable. And those were deployed in Nigeria, Singapore, and California for this first launch. Soon after, NASA, the National Aeronautics and Space Administration, was formed properly. At the time, the foremost propulsion engineers or rocket scientists in the country worked for Caltech at JPL. So NASA contracted with Caltech to make JPL a federally funded research and development center, and it remains under that designation all the way through to today. So JPL is in charge of our DSN contract. So next slide. These days, we're not using mobile tracking stations anymore. We're using fixed antennas, really huge ones. I'll talk about the size of them on the next slide. But we have three stations. So Goldstone is here in California. It's on the Fort Irwin military base up in the high desert. We have one near Madrid in Spain and one near Canberra in Australia. And what you'll notice is that these stations are separated by about 120 degrees on the globe. So as the Earth spins, we have continuous view of all parts of space because our three stations are equally spaced around the globe. And so the big dotted line right here, this is geostationary orbit. So what you can see is we have an overlapping view from Goldstone and Canberra at geostationary orbit and beyond. Below that, we face a couple of issues. One, the spacecraft come across the sky too fast for our big antennas to move and track them. But also we have big visibility gaps where it goes out of view of one station, but it doesn't come into view of the next station for a long time. So that's why we go geostationary orbit and beyond.
Can I ask you?
Yeah.
When you say geostationary orbit, the satellite's traveling, but it's traveling at the same speed as Earth?
It's rotating.
Yeah.
So it's over the same point on the Earth at all times.
Okay.
And that's just a set distance.
Right,
So
right.
we say geostationary not necessarily because it's geostationary, but it's a set distance from the Earth.
Right. And it's obviously moving very fast, but we can't see that because it's sitting there all the time.
Directly over.
Yeah.
All right. So The cool, actually, two times it's got stuff that comes out. I don't know why there's animations in this. But the one thing I wanted to talk about here is the long distance call. So you might make a long distance call on the Earth, and that's all the way over to another continent. We make a long distance call to the Voyager spacecraft. And so I checked this 22 and a half hours, the round trip light time from Voyager to Canberra yesterday was 46 hours, 18 minutes, and 42 seconds. So what that means is we send a signal from our antenna, and it travels for 23 hours at the speed of light to get to Voyager. Voyager receives that signal and sends us a signal back, and it travels for another 23 hours back to us. In the meantime, the Earth has completed 2 rotations, and we're receiving that signal 46 hours later. So we're 24/7, 365. There's no holidays at the DSN. We are receiving data from spacecraft every day of the year, every hour of the day and night. As Vaughn will attest, we don't operate on earthly schedules. We operate on celestial schedules. So if it's happening at 2 in the morning, we're working. Yep.
So when you say 46 hours, that's the 15.2 billion miles away?
Yeah, 15.2 billion miles.
Yeah.
That's all?
Yeah, that's it. It's almost the same mileage your car had.
Click the next one. So our largest antennas, we've got one at each of our 3 complexes, are 70 meters across. So bottom left there, that's what a 70-meter antenna would look like in the middle of the Rose Bowl. So these things are enormous. And if anybody can recognize this football field, I couldn't identify this one. I don't know.
Chris?
I'm gonna guess Ohio State.
Okay. That might be the O.
Sounds good.
Sure. Anyway, just to impress on you just how big these antennas are.
It's amazing.
You know, I like to say you could play a game of football in that dish, and here you can see it.
Only last. What's the last special roughly?
It's not well known. There's only 3 of them, and we haven't retired one of them yet. So we kind of, when they break down, we repair them. And we, a lot of times this is like one-of-one type parts. So when we need a replacement, we make another one-of-one type part and replace it.
These are from the 50s?
Let's see. The 64-meter antennas were built in the late 60s, and then in the 80s they were expanded from 64 meters to 70 meters. They made the dishes bigger.
Now, these dishes, do they turn to track things, or?
Yeah. So this is a cool element of how this works. So right here in this gap, this is called a hydrostatic bearing. So actually the entire antenna floats on a film of oil. So there's high pressure oil pumps that lift it up, and then big gears that rotate it. And so our antennas rotate in azimuth, which is like 360 degrees around the horizon, and then elevation, which is 0 degrees to 90 degrees straight up.
Oh, wow.
So pointing at any part of space can be expressed as an azimuth and an elevation. All right, so I didn't connect to the Wi-Fi, so we can't open it up here, but I recommend you guys take a Google for NASA Eyes or Deep Space Network Now. This is a real-time display of what we're tracking with each antenna. So you can see in this case, here was DSS 55, Deep Space Station 55 at Madrid, talking with the Psyche spacecraft. And you'll see signal either coming up out of the antenna, that means we're transmitting, or signal coming down into the antenna, that means we're receiving. But at any time you can go look and see what we're tracking with the antennas of the Deep Space Network. So if anybody used their mobile phone to pull it up, you might see it.
So can one of these antenna only transmit a single communication at a time? Or are they transmitting constantly, sending people all over the place?
So the antennas are highly directional, meaning we can really only point them at one part of space at a time. And then as far as the transmit, we can transmit to one spacecraft at a time, but we can receive from many at once. So for example, at Mars, there are 8 different spacecraft between orbiters and landers on the surface. So when we talk with Mars, we point at Mars and we receive data from all of those spacecraft at once, but we talk to them sequentially. So we'll talk to spacecraft A, then B, then C, then D.
How many spacecraft total do you?
About 40.
40?
Yeah.
Give or take.
Give or take 40. About.
Yeah.
So the Voyager, let's say, I'm not sure how big the Voyager is, but it's way out there, right? So if you're tracking different satellites, how hard is it to get back onto Voyager? I mean, you know what the path is, you know how far it should go, but what if it hits some sort of thing out there and it moves it? How hard would it be to find it again?
I think the part of that is to hit something that moves it. If Voyager hits something, there would be no more Voyager. It's going so fast that if it hit anything, Voyager would be in a million pieces.
Gotcha.
And we call Voyager our DSN star because these days it's so far out that its relative position doesn't move much. It acts like a star.
Gotcha. Okay.
So if you want to talk to Mars, you have to predict where it's going to be when the signal hits it. Ahead, right? I'm talking to one of the rovers. It's going to take 23 hours to get the signal.
Yeah, so Mars is anywhere between 6 and like 25 minutes to get there, and it's not really an issue. We don't have to lead it necessarily. All right, go ahead. Oh, yeah.
You said you were tracking 40 spacecraft plus or minus. Are those all U.S. or do you track foreign spacecraft?
Some foreign spacecraft. Really the rule is no Chinese spacecraft. We don't track anything from China, but most other nations we collaborate with. So we've done spacecraft from India, from Japan, from Korea, from Israel, from the United Arab Emirates, so a lot of different countries.
And East in Europe.
Do you have contracts?
No, but they have their own space. Roscosmos.
So with many of these
Similarities,
nations, it's
but we don't
a trade on tracking hours. So with the European Space Agency, as many antenna hours as we give them, they give us.
But we don't
With
track their space.
They do. There's a European tracking network, and we share time with them. In many cases, they'll actually cover visibility gaps that we have. So, especially things that are up near the poles, we don't have great visibility because you think about California and Madrid are mostly near the equator, right, or pretty close to the equator. So if something's way up north or way down south, we don't have good visibility, but Europe has better stations for visibility in those areas. So we trade tracking hours.
Okay.
Yeah. I'm not sure exactly how it works with Japan and the United Arab Emirates, but what I know about those missions is they're mostly collaborations between NASA and that other agency.
We collaborate with the Russians.
Only on the space station.
Only on the space.
Only on the space station. There is no other collaboration in NASA anymore.
We don't track their space.
Europe used to collaborate with them more, but now all of that collaboration between Europe and Russia is also gone only on the space station.
Does China surveil us?
Probably. I don't know exactly.
At times, if I may, when we track certain spacecraft, at times we'll see what they call RFI, radio frequency, like interference, frequency interference, and we have engineers that work specifically with RFI issues, and some hypothesize that some of that interference, for example, at Mars, is from It's called the Tiananmen spacecraft, which is
No,
Chinese.
Tianwen, not Tiananmen, Tianwen.
Tianwen. And so we do think that happens.
Yeah, it's not intentional necessarily that we can tell, but
Yeah,
it
not
happens
Tiananmen.
between our spacecraft as well.
Tianwen.
I wouldn't bet on that.
All right. So now I'm going to talk about some spacecraft that we track, some of the missions we work on. This first one is MAVEN. This is the Mars Atmosphere and Volatile Evolution mission. So it was launched in 2013, so it's a little bit older compared to some of the others. But the purpose of this is to study the Martian atmosphere. And the part of this that I find really, really cool is that these wings here, they're a solar panel on this side. But the other use that they have is they use these wings to surf in the atmosphere of Mars to measure things like the atmospheric density. How dense is the atmosphere of Mars? But the thing that I find that illustrates the kind of work that we do is that after they do one of those dips down into the atmosphere where they surf through it, the density is the unknown quantity there that they're trying to measure, but that density also affects how fast the spacecraft is flying. So when it comes out of that deep dip into the atmosphere, its orbit is different. And the only way that they can know how the orbit is different and what kind of maneuver they need to do to recover the spacecraft to a good orbit is by our tracking data. So after they do one of those deep dips to collect their science data, we have to get extra tracking data to make sure they know where the spacecraft is and how it's orbiting Mars. So that's the kind of concern that we have to worry about as ground stations tracking these spacecraft.
Are you just picking up the new orbit, or are you adjusting it? Are you sending
So
information to change it?
we would collect the tracking data. There's another team that operates this spacecraft. So they would design a maneuver, give us the commands to send back to the spacecraft to adjust the orbit. Let's go to the next slide. So I talked about 40 spacecraft. I counted this, it's 33, and some of these have been retired, so it's not an up-to-date picture, but 40 spacecraft currently tracked by our network, roughly. So I wanted to talk a little more about the Voyagers. So 1977 was the launch of Voyager. And if you want to know the kind of technology that's on Voyager, it's about like a TI-84 calculator connected to a VCR machine. That's about what the technology on Voyager is. It communicates to us at 10 bits per second. That's 10 to the 6th times slower than your cell phone. And we have to maintain compatibility with Voyager while we also develop the new capability to talk with the latest spacecraft from SpaceX and Blue Origin and human spaceflight. And it's a unique challenge that we have where Voyager is a national treasure. We gotta keep it alive. We're gonna keep it going as long as possible. It's a radioisotope generator, a radioisotope that's decaying, generates heat on board, has been slowly decreasing in performance over time. So they've been slowly turning off instruments, but we're still communicating with it. 46 hours round trip flight time. So this is kind of our DSN star, like I said. Let's go to the next one.